dropout is basically a kind of ensemble. So here we can divide the training set into mini batches. So set 1, set 2, set 3, set 4. So these are the 4 training instances, and for every training instance we are using different set of training samples. So by using while using set 1, we thin the network by randomly dropping out some nodes. Similarly, for set 2, we use another network architecture where some different nodes are dropped. Similarly, for set 3, we can use another thinned network, and same for set 4. Okay. So these are the 4 training instances where we are using 4 different networks. Why they are different? Because randomly we are dropping certain nodes. Okay. So train a bunch of networks with different structures. Okay. So we train number of networks. Okay. Using some training samples. So while testing the data, what we do? We have actually 4 networks, but while testing, we don't use these separate networks, but we use all the nodes. Okay. And we get the outputs y1, y2, y3, y4 if they are different networks. But as we combine all these networks, we use all the nodes by appropriate scaling of weight. So we effectively get average of these 4 outputs. Okay. So using the entire network without dropping any nodes and scaling the weights, this is equivalent to getting output from all these 4 individual networks and taking their average. Okay. So we call this dropout as a kind of ensemble. So say this is mini batch 1, and say we are using these particular nodes for mini batch 1. For mini batch 2, say we are dropping some other nodes and we are using these nodes. For batch 3, we can have 3rd different network as shown here. Okay, so these nodes here, these are dropped. And during mini batch 4, these middle nodes are dropped, and we are getting this different architecture. So for if there are m number of neurons, there are actually 2m possible networks. We don't go for all these possible combinations, but we select few of them by dropping certain units. And we use set of training samples, subset of training samples to train each of these networks. So some parameters in the network are shared or they are used multiple times. So during testing, we give this testing data and we take average of all these outputs, or this thing is equivalent to this. So we use the network instead of using 4 different networks. During testing, we use the complete network with all nodes and we scale the parameters or weights by 1 minus p%, where p% represents a probability of dropping the node. Okay. So if p is probability of dropping, then 1 minus p is probability of retaining the node. So that's why we scale the weights by 1 minus p%. Okay, so finally we get output y, which is equivalent to average of these output from these 4 different networks with which we have trained the network. Now, so one more issue with deep neural networks is computational load. Why? Because your deep neural network has large number of nodes and hence large number of parameters. So it requires more calculations are required for large number of neurons and large number of hidden layers. So high computational overload and network gets low. So to avoid this, what we can do is, solution is we can go for high performance processor like GPUs and efficient algorithms like batch normalization. Okay. So this is an example. We can train a network, deep neural network, to recognize handwritten digits. So for this network, you can have, say, uh, x1 to x256. These are different inputs. Okay, and this is your network which is trained for given inputs to recognize, say, digit 2, or if as there are total 10 digits 0 to 9, you will have total 10 number of classes at the output. So there are total 10 output nodes, and x1 to x256, these are the input features. So in deep learning, the function f is represented by your neural network. So we apply this neural network on the input data so that your given input digit is classified to one of the given classes. Okay. So now we are going to next part of the lecture, that is basically how the deep neural network architecture looks like. Then what is convolutional neural network? What do you mean by convolution layer and polling layer? And then we will be having a look at various convolution neural network architectures. Okay. So as the name indicates, deep neural network means there are large number of hidden layers. So your network, say network input has A1 to AK as input features. So at hidden layer you have nodes, and at every node you get weighted addition, and there is one more input, that is bias term. So this node is similar to your basic node of conventional neural network. Okay, so it gives some output Z, which is weighted addition, that is A1W1 plus A2W2 up to AKWK plus bias term B. So this is your net output from the node. So this is as shown here, Z is given by this equation. And then we apply some activation function on Z to get final output A. Okay. So we multiply inputs with respective weight values, then we determine Z by weighted addition, we add to this bias term, and then we apply activation function to get the final output. So in case of deep neural network, there are multiple hidden layers, and number of hidden layers is usually more than 5. And in every layer, there are number of neurons. Okay. So here you have this input layer where input features are indicated as x1 to xn. This is your output layer where you have outputs y1 to yn. And all these, your blue, red, green, these all are hidden layers, layer 1 to layer L. So these are hidden layers, and this is your layer L is output layer, and from this you are getting outputs y1 to yn. So deep means there are many hidden layers. So at every layer, we can compute output from individual nodes. So say if these are the weights and these are the inputs, if input is 1 minus 1, and the weights for hidden neuron were 1 are 1 minus 2, for second one these are minus 1, 1. Here bias term is 1, and for second hidden neuron bias term is 0. Then we will get weighted addition as shown here. And then we can apply sigmoidal function on this to get the final output. Okay, so for this case, final output is 0.98. and here you get weighted addition as -2, and when you substitute this -2 here, you will get this output of sigmoidal function as 0.2. Then these are the weights for next layer. You can, and again you can apply sigmoidal function on net output, and you get some output 0.86, 0.11. Then similarly at third layer you have these weights, and this will be considered as inputs. Okay, and then you can determine actual output from this layer, and you can continue this process for next all hidden layers. Okay, so if inputs are 0, these outputs will be different. Okay. So we can perform all these computations in matrix form as shown here. Instead of determining individual outputs, we can do it in terms of matrix. Okay, so for F1 minus 1, output was different and than that for input 0, 0. Okay, so for 0, 0, it is 0.51, 0.85. For input 1 minus 1, it was 0.62, 0.83. Okay, so different parameters define different functions. And as shown here, we can do entire calculation in terms of matrix. So this weight matrix multiplied by input parameter gives us output, a vector for which represents output from this hidden layer. Okay, so this vector is for bias 1 and 0, and then we apply activation function on this to get this output 0.98, 0.20, 0.12. Okay, so basically we have a matrix of all weights that is represented by W matrix. So for very first layer, input layer and first hidden layer, weights are indicated by W1. X is your input vector, B is your bias vector, and then we multiply W1 with X1, with X, we add it to B1, and then we apply activation function on it. So this is same as your conventional neural network. So we get these outputs here for layer 1. Then W2 represents weights between first hidden layer and second hidden layer. So again, we can represent it in matrix form. W2 multiplied by A are the outputs from previous layer. So plus B2, that is bias for these neurons. And then we again apply activation function. And then we use similar process at every layer. Okay. So in general, at L layer, we have sigma of WL into AL minus 1 plus BL. Okay. So this is equation in matrix form to determine output from any layer of this deep neural network. Okay. So we can represent final output in terms of previous layer. Okay, so this previous layer's output is represented in terms of previous layer input and weight, and so on. So finally, we will get some equation like this. Sigma W2 is equal to sigma W2 multiplied by sigma W1x plus B1. We multiply it by W2, then we add it to B2 to get sigma. And similarly, there will be L number of layers, so we can represent final output as shown here. Okay. So here, in order to speed up the process, what we can do is we can use parallel computation platform so that we can parallelly perform desired operations. Okay. And we can reduce the time of network training. So these deep neural networks come in a wide variety of shapes and sizes. And depending on application, we can use particular architecture of DNN. The popular shapes and sizes are also evolving rapidly to improve accuracy and efficiency. In all cases, input to a DNN is set of values representing the information to be analyzed by the network. So for instance, when we are doing some object recognition from images, these input values are nothing but the pixel values. If we are performing some application related to our audio, then these are inputs are nothing but sampled amplitudes of an audio waveform, or it can be numerical representation of the state of some system if we are designing some games. Okay, so according to application, your input data will vary, type of input data will vary. The network that processes the input come in two major forms. So in a broader sense, we can classify DNN architectures into two types: feed forward networks and recurrent networks. So in feed forward networks, all of the computation is performed as sequence of operations on the outputs of a previous layer. So as we discussed just now with this example, uh, we compute output from this layer, we pass it to the next layer. Again, we compute the output from next layer, we pass it to next layer. Okay, so here, in case of feed-forward networks, we perform a sequence of operations on the outputs of a previous layer. The final set of operations generates the output of the network. So your final layer is output layer, which gives you some output. So for example, this output might represent probability that an image contains a particular object, or it can represent probability that an audio sequence contains a particular word, or it is a bounding box in an image around an object of interest, or it is proposed action that should be taken. Okay, so again, according to application, your format of output will vary, or interpretation of output will vary. So in such feed-forward deep neural networks, the network has no memory because it processes present output from previous layer. Okay, so it doesn't need any feedback, and hence there is no need of memory. The output for an input is always the same, irrespective of the sequence of inputs previously given to the network. So output at any given instance, it does not depend on previous inputs. Okay, it depends only on the present input. Okay, so this is meaning of feed forward network. Then in recurrent networks, in contrast, recurrent neural networks have internal memory to allow long-term dependencies to affect the output. So in case of recurrent network, there is feedback from output to input, and your output at any given instance, it depends on present input as well as previous input and past outputs. Okay, so it needs some memory, and one of the popular variant of recurrent deep neural networks is long short-term memory networks. Now in these networks, some intermediate operations generate values that are stored internally in the network and used as inputs to other operations. So at certain given instance, whatever inputs or results of certain operations, they are stored in the memory and they are used in the next operations. Okay, so this is a type of feedback network or recurrent network, and it basically needs some amount of memory. Now let us see, what do you mean by fully connected deep neural networks? So DNNs can be composed solely of fully connected layers. So in case of DNN, you can have all nodes from one layer, they are connected to each and every node of the next layer. So in a fully connected layer, all output activations are composed of a weighted sum of all input activations. That is, all outputs are connected to all inputs. So this requires a significant amount of storage and computation, right? So here you need many number of parameters or weights. So you need to store those parameter values, and you need significant number of computations because all the nodes are connected means you need to take into account each and every product term. Okay. So thankfully, in many applications, we can remove some connections between the activations by setting the weights to 0 without affecting accuracy. Okay. So in a case of real applications, we can remove certain connections or we can make the weights 0. Weight is 0 means as if you are removing connections from that particular node. Okay. So what is advantage of removing certain connections? Basically, when you remove certain connections and when you use a thin network, number of computations will be reduced. Okay. So this results in a sparsely connected layer. So how we can reduce number of computations and amount of storage? So we can also make the computation more efficient by limiting the number of weights that contribute to an output. So instead of connecting all nodes, instead of having fully connected layers, we can avoid certain connections. Okay. So this sort of structured sparsity can arise if each output is only a function of fixed size window. So instead of connecting every node from input layer to output layer, we connect particular node along with its neighbors to one particular output node or node from the next layer. Okay. So this is required in order to reduce the amount of computation. Okay. So even further efficiency can be gained if the same set of weights are used in the calculation of every output. Okay, so to further reduce amount of storage, what we can do is weight matrix. Say we are selecting particular window or all the nodes in one particular window if we are connecting them to one particular output node, and in that window we are using some weight values, say W1 to Wn, then same weight values can be used for all other windows. So this is known as weight sharing. Okay. So because of weight sharing, it significantly reduces storage requirements because for all the windows we are using same weight matrix. Okay. So this leads to reduction in the storage and reduction is in computation because we are now not using fully connected network, but we are using a node and some neighborhood or some nodes under a window. Those are connected to one particular output node. Okay. So this gives rise to convolutional neural networks. This last statement where we are sharing weights for different windows, and instead of using full connections, we are simply connecting nodes from particular window. So this gives rise to convolution neural network. Okay. So an extremely popular windowed and weight shared deep neural network layer arises by structuring the computation as a convolution, where the weighted sum for each output activation is computed using only a small neighborhood of input activations. That is, all weights beyond the neighborhood are set to 0, and where the same set of weights are shared for every output. So under every neighborhood, we use the same weights. Okay. So it is as if applying some theta function to the given input. Okay, so such convolution-based layers are referred to as convolutional layers. And a network which makes use of these convolutional layers is known as convolution neural network. So let us talk more about convolution neural network. Let us take break of 1 minute, and during that I request all of you to type your attendance, your PRN numbers followed by space and your name. Please type your attendance and don't leave the meeting. I'm just taking break of 1 minute.